So anyway, cute little cartoon for everybody. Okay, come on. There we go. So this is about where we finished off. I want to talk a little bit more about total dissolved solids. Last day we were talking about them, and I had mentioned that you know, besides the obvious properties that we talked about, hardness and alkalinity, they can also alter taste, right, and make it kind of salty. So the cutoff is around 500 parts per million. So if the water is 150 or 300, it's fine, but when it gets around 500, it starts to taste salty. So this is something we're concerned about with drinking water, obviously. And I think, did we talk about this slide? I think I'd mentioned some of the things that might contribute to total dissolved solids. You know, the obvious one is human types of pollution. So that could be road salting in the wintertime, could be various industrial processes, but there's lots of natural processes that are going to contribute to total dissolved solids. So, you know, the river is flowing along and picking up all sorts of things as it's going. And so you can end up with all good on there on that end? Maybe somebody just turned the microphone on by accident. What else is it going to talk about? So there's that number 500. So I can't remember if I finished off talking on this last day, but I wanted to relate this to our lab this week. And so you're going to get a chance to use these conductivity meters. So conductivity and total dissolved solids are directly related. So conductivity is just how much electricity can go through a solution. And so the more ions you have in solution, the more likely it is that the electricity is going to go through. So it's not a perfect measurement, because you might have neutrally charged substances that contribute to the total dissolved solids, but it's a pretty good approximation. So I can't remember exactly what the approximation is. It's about 600, I think, microsiemens per centimeter is 1,000 ppm or something like that. The conversion I found is it's in your lab manual. So rather than measuring the total dissolved solids, we can get conductivity pretty much instantly from using the conductivity meter, and then you can make a conversion. So that'll be part of your lab this week. So all good? So that's water chemistry. So we will come back to conductivity and total dissolved solids later. And now we're going to talk about, my button's too fast, let's try that. There we go. We're talking about water biology. So great picture, eh?
Yeah, a pike.
Yeah, I found this, I can't remember how I found it, somewhere on the internet, one of those photography contests or something like that, and I thought that was a really beautiful picture. You can see lots of really nice, you know, marine and ocean fish photographs, but you don't usually get necessarily these nice freshwater ones, right? So are there lots of pike around here? I would imagine. I don't.
Yep. Yep. Whenever my uncles go fishing, pikes are usually one of the fish they usually catch.
Yeah. Okay.
And you know, fun fact about pike is that even though they're fish, people don't really eat them all because they're very bony.
Yeah. You know, I don't fish so much anymore. I did a lot more when I was a kid. But when I go to Ontario, my brother-in-law, like, until he had kids, like, you know, he would have a fishing rod in one hand, like, constantly, right? Anyway, he knows how to clean them, right? And there's some special way you clean them, and they're very tasty. They're just as good as walleye. But anyway, yeah, sometimes they put up a good fight too, which is kind of nice. So water biology, what are we talking about? All of these things here, right? There are all sorts of potential things that could live in the water. We're not going to talk so much about plants. We're going to talk a little bit more about these things that I have stars beside. And so what I want to talk about a little bit is about, you know, things that are going to make us sick, things that are going to affect water quality, right? So that's kind of the focus on this whole thing. I have the euglena here. Do you guys look at euglena in Biology 108 as one of the specimens?
We look at E. coli.
Euglenozoa. Yeah, these ones are very cool. Protists, they've got flagella, so they swim around, and they have chloroplasts, and so they're not really a plant or an animal. They're kind of a good definition of a protist, just weird. But I like them. I think they're pretty cool. So anyway, like I said, we're not going to talk about necessarily everything that's in the water, but this is kind of the breakdown of the list here. So we're going to talk a lot about, like I said, waterborne diseases and some of the different things that can make us sick that we're concerned about. And most of these things, by the way, are the same things that might make us sick from contaminated food as well, which makes sense, right? These are things we're ingesting, water and food, right? We're going to talk a little bit about analysis of water in terms of looking at the microbiology kind of analysis and why that's important, and a little bit about these things here. So other things that might make the water undesirable, biochemical oxygen demand. I know we're ahead on the labs at the moment, and then wastewater treatment. Just a tiny bit of a preview because it's going to come up actually in topic 10, which is a lot more detail on that. So let's talk about waterborne diseases. We don't see this as much in Canada. For the most part, we have good sanitation programs in Canada. When you get to more remote areas, I know there's a lot of Indigenous communities in Canada that don't have proper water treatment, and you hear about that a bit more in the news about people getting sick from contaminated water. Sometimes on farms. Most farms have well water, and of course you've got lots of animals with manure that can cause issues once in a while, depending on the layout of, like if your fields are up here and your house is down here, right? You can imagine just the flow of manure, which is not usually the best idea to have that kind of thing set up, but we don't always get to choose what's going on with our property, right? We make the best of it. So most of these waterborne diseases are directly connected to feces, right? Hopefully that makes sense. That's where we're getting most of our pathogens that are ending up in our water are from feces. So three kind of sources. Can you think of what they are? Three sources of feces? Humans, yeah. Animals. And I'm thinking two types of animals. So I'm thinking farm animals and then wildlife, right? So I kind of categorize them as two different things, because particularly farm animals in particular can produce a lot of it, right? I don't know where I would fit dogs in there, but that happens sometimes too, right? Dogs, of course. So you can see in this case here, this happens once in a while. You can see this image we've got that somebody has an outhouse, or it could be a septic field or something like that, and their well is too close, or the leakage gets in there. So usually, when this is assuming some sort of farm or something, you're going to have those things in, different sides of the property is the whole idea. But it is something that does happen. And anyway, you can use your imagination about all the different ways feces can get into water. I'm trying to remember, no, it wasn't you guys. I was talking to my other class the other day. I was reading a book by a microbiologist, and he was talking about going to Mexico, and he's at a resort and enjoying the beach, and decided to go for a little stroll kind of away from the resort. And what did he find? A pipe. And what was coming out of that pipe? It was the sewage, just being dumped directly into the ocean with no treatment whatsoever, right? So you can imagine that in a lot of countries, this is the norm. And in fact, there are places in Canada where we do that. Up until recently, and they might still be doing it in Halifax, that was the system. Right? By law, they have to do something about it, but I can't remember what the timeline is, right? But there were still several communities in Canada that were doing that, basically dumping sewage into the ocean. So, like I said, you can imagine the variety of things going around in different countries, and some of these diseases can be very, very serious. So just some numbers and things like that, right? So I got this from Stats Canada or something. They're estimating, maybe around 90,000, 100,000 cases from waterborne diseases in Canada. It's kind of hard to measure because a lot of them go unreported, right? People have, people get sick, they have diarrhea. If it's not bad, you stay at home, right? You don't usually go to your doctor. but maybe about 90 deaths. So that's not a huge number, but lots of illnesses. Some of them in daycares and you know, old folks nursing homes can be a little bit more serious. In terms of human disease worldwide, it's a little bit more significant. And like I said, that's directly correlated to the fact that a lot of places don't have the same water sanitation as Canada does. In Canada, one of the maybe highest publicized breakouts was in the year 2000 in Waterborne, Ontario. So I can't quite exactly remember where Waterborne is, but I'm from Ontario, and I remember this at the time, and there were, does it say how many people? Yeah, 2,500 people became ill. I think the town only has double that, you know, or triple that or something. So it was like, you know, maybe 30 or 50% of the town got sick, and 7 people died, right? This doesn't happen all the time in Canada. So we'll talk about Waterborne and what happened there. Probably won't get there today, but next day. So that was really significant. So if we look at infectious diseases, in terms of, we're talking about the globe, you can see that right there, number 3. Number 3 on the list is diarrheal diseases, right? So interesting list though, because these are things we're not necessarily dealing with all the time in Canada. Certainly people do get AIDS in Canada. People do get tuberculosis, but it's small. The numbers are small. Like in terms of HIV infection rate, it's like something like you know, 0.4% of the Canadian population.
Fun fact about tuberculosis, you know who Shauna Devitt was?
I don't know. No.
She was the last of the First Nations people called the Biothic, and how she died, and tuberculosis was the reason for her death.
Yeah, actually a lot of famous people died from tuberculosis. If you ever watch movies, and they're like historical type movies, you know, that take place a couple hundred years ago, sometimes they talk about people dying of consumption. And by that they mean tuberculosis. Because when you have tuberculosis, a lot of people, they just don't eat. They just don't feel like eating because they feel so sick. And then they waste away as part of the disease process. But you know, malaria and measles, you know, these things happen, but not so much. We do get respiratory infections in Canada. We do get diarrheal diseases in Canada, but we have pretty good health care. And so usually they're not fatal, but in many countries they are. And you can see on this chart, it's making a distinction. You can see the big blue bar on there is showing that for people under 5 in some developing countries, this is a major cause of death. Apparently, according to that number, it's about 9% of death. So that is very, very significant. So sometimes we have breakdowns, and sometimes it has to do with natural disasters, right? So we know at Fort McMurray here, you know, when we had that flood, there was a boil water advisory for, well, I don't know how long. Yeah, I think it was threatened to be all summer, but it turned out it wasn't that long, thankfully. And so, you know, but these things happen all the time. You can see there's this talking about El Nino, which, is it another El Nino year? I thought I saw that in the news. It's coming up again, maybe. So that's, I don't know a lot about El Nino, but it's cyclic and it's these big storms. And so it's linked to disease incidents in a lot of Caribbean countries, you know, when it comes. It seems to go up. Hurricane Katrina.
2005.
So that was 2005, New Orleans. They had major, a huge amount of disease just due to water systems getting contaminated.
You know when have you ever heard of Hurricane Isaac? I think it was like the 7th or 8th year anniversary when Hurricane Katrina struck, and on the same day Hurricane Isaac like struck as well.
Exact same day. Go figure, right?
And Isaac was as dangerous as Katrina, but I'm just.
Yeah, I don't remember Isaac as much though. Yeah. Another one that I remember quite clearly was Haiti. That was 10 years ago now, and they had gone, I think it was something like 70 years without a single cholera case. And somebody came to Haiti with cholera basically at the exact same time as the earthquake. And because of that, suddenly there were 200,000 cases. Because suddenly no access to clean water. So these things happen all the time, right? With you know, linked to you know, just failures in water sanitation, right? So during the fire, the Fort McMurray fire, by the way, one of the few places that was manned the entire time was the water treatment plant. And because their concern was if no one was there manning it, they would have to shut it down. It would take months to get going again, right? So they made sure somebody was there manning it the whole time. So I guess we answered part of this question. How do we control these diseases? Water treatment. So water treatment, water testing, and other normal sort of preventative measures. So things like vaccines and healthcare, things like that. Those are kind of the main answers there, right? Sanitation, treatment. That's another good one. Protection of water sources, right? So we want to make sure, and you know, this is very important, right? You know, if we're living here in Fort McMurray, and it's very important that we treat our water because there are people that live downstream from us, right? You know, the river goes up past Fort McKay up to Fort Chip. So it's very important that we treat our water so that we don't contaminate them as well. A lot of places have man-made lakes or reservoirs for their water, for their city. And it's important to protect those. So a lot of those will have fences or other protections so that, you know, we're not having, you know, contamination go in there. New York City has a natural reservoir that they use for their water treatment. And they have to keep deer out of it because the deer go in there and they poop, right? So I think it's a big fence is my understanding what to do there. So what kind of things are we talking about that can make us sick? We are going to talk about these things, but we're going to talk about them mostly next day because I want to talk about the tests in a minute here. But these are the usual suspects. So hopefully you know what these things are, right? Biology 108, you would have talked about most of these things to some degree. We're going to review what they are now. Fun fact, this is maybe the #1 reason why I threw out the textbook for this course. There was a textbook I used for a couple of years, and they kept calling bacteria plants. And I wrote to the publishers. I actually wrote them a letter, and I said, you know, like, the least you could do is have somebody proofread your textbook because this is garbage. And then a new edition came out, and there was no change to that, right? And I think the textbook was written by an engineer, so somebody familiar with, you know, pipes and pumps and hydraulics, but had not researched their chemistry and biology. So it was really, I mean, there were just mistakes like that all over the place. And in the end, I couldn't find anything really that suitable. So I think it's just better to do the way we're doing it. But yeah, these are the usual suspects. Bacteria and viruses being the big ones. Algae don't usually make us sick, but they can make water kind of putrid. Or they can kill fish if you have like an algae bloom. You can suck out the dissolved oxygen into that. And we'll talk a little bit about parasitic worms. They're usually more important in other countries, but there is one that some of you may have been afflicted by that can cause a swimmer's itch. So I've had that at least once, maybe twice. It was not much fun. So anyway, we will come back to this. What I want to do now is talk about the test and go through a sample problem, right? So the test is next Monday, okay? And it's going to cover basically the water hardness up until right here, okay? So a little bit of this water biology stuff, right? So, you know, make sure you can answer some questions about some of the things we just talked about, right? In terms of, you know, what is the major contamination of water? It's feces. The three possible sources, you know, those kind of things. So just some general stuff. I'll probably find for that it's probably not going to be more than maybe 3 or 4, you know, multiple choice, true, false kind of questions. And then the rest will be focused on this chemistry stuff. So don't forget, we did talk about dissolved gases. We talked about colloids. We talked about organics that can end up in water, and there might be a couple other things in there in between as well. So make sure you take a look at those notes. But out of 20 marks, about 10 marks will be a water analysis question. Okay, so I have one for now. Any questions about this?
Will we have to like draw a bar graph?
Yes, you will. Yeah. So I'll show you what the question will look like. It's going to be something like this. So I think this is one I scooped up off a previous test. Okay, so you know, maybe I'll ask it slightly different, but questions will be very, very similar. Okay, so you can see you've got a water analysis, and it's you've got some ions listed there. I'm giving you the concentrations that came out from the analysis and the equivalent weight. Okay, so here's the kind of questions, right? And so, you know, the first one, we'll go through these one by one, is we're converting everything to the milliequivalents per liter, right? So that's the first one. I'll just go here to this next slide. And so I don't expect you to show me all of those, but show me one sample, okay? Because if there's something wrong with with that, I would like to show you to show me one sample calculation. So let's do one. Remember the formula. Hopefully I didn't do anything there to somebody. It beeped on me. So the formula is milliequivalents per liter.
Milligrams per liter.
Is milligrams per liter divided by equivalent weight. Okay, so for calcium, we'll do calcium is 185 milligrams per liter. How's that showing up? Not too bad. I'm getting better at writing on the screen, but it's not as nice as writing on other things. All right, and then equivalent weight is there, and it's 20 milligrams per milliequivalent. Okay, so you can see the milligrams are going to cancel out. So the answer I'm going to get is 9.25 equivalents per liter. Okay, so boom, 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 boom. You're going to punch those on your calculator. They're all lined up there. I've left some room in the table for you to fill in all the answers so you can see it all in one place. And there's my reminder to you to please show one sample calculation so that I can give you part marks if you do get something wrong. Okay? So there's all the values that I got. All good? So notice we're not calculating anything for the calcium carbonate. I just threw that in the table so that you have the equivalent weight for the later questions. Okay, so I meant to actually box in, I was going to fill this in and fill this in, just so nobody tries to fill those ones in. Okay, so what was the second one? The second one is draw a milliequivalents per liter bar graph. Okay, and so I'll see if I can get some rulers. So I have some spares. If anyone doesn't have a ruler, I know not everyone necessarily has one. We have a big box full of them downstairs in the environmental lab. So what you want to do is, you know, tell me what your scale is, okay, and then you're going to draw your bars, okay. So you're going to put all the cations together, and there's calcium, so this will be, you know, 9.25 centimeters or 992.5 millimeters, I guess, right? So, you know, I don't know if that's necessarily the scale. I just built it in the PowerPoint, and tell me the units, right? So you're going from 0 to 9.25, and so the magnesium is next. And the magnesium is 3.93. So you can see I've added them together, right? 9.25 plus 3.93. That gives me 13.18. And then I'm going to add the sodium. So then we can do the cations. Okay, so the cations, anions are the negative charges. And we have bicarbonate. So notice, by the way, they're not in order of quantity. Okay. So you can see that the sulfate is actually the next one. So usually the convention is you're going to do things in order of quantity. So the next largest quantity is actually the sulfate. So I added up the bicarbonate and sulfate, it gives me 9.88. When I add the carbonate, I get 12.16. And I've added the chloride, and so I'm getting up to 13.51. Question? So they don't add up. All right, that's the next question. So anyway, that's what it's going to look like, and I've even color coded them just for fun, but you don't have to color code it. So make sure you use a ruler. You make it neat and pretty. It's easy marks, but you know, just I want you to show me that you know what you're doing. maybe it's not the next question, maybe it's D. We'll get to that in a second. So this says list all the hypothetical combination of compounds for sulfate. Okay, so what I want you to do is tell me all the possible sulfate compounds you're going to get. So basically, you're going to combine sulfate with, so the first one is calcium. So we've got calcium and sulfate have complementary charges. So it's going to be CaSO4, and then magnesium. So magnesium sulfate and sodium sulfate. So in this case here, we'll need 2 sodiums to balance out the sulfate. So that one should be easy too, right? Just some standard kind of introductory chemistry stuff. All right, so D says calculate the balance error and give one reason why the concentrations are not equal. Okay, so the balance error, remember, is this formula here. So you're basically subtracting the cations and the anions, or the other way around. It doesn't matter. I just want a positive number. It doesn't matter if it's a negative or positive. And then divided by the sum of them, right? So the cations plus the anions. And then times 100 to get a percentage. Okay? So in this case here, you go back to my graphs, you can see those were the numbers that came up. The cations are 15.4 and the anions are 13.5. So I subtract them and then I add them together, multiply by 100, I get 6 point something. So 6.57%. And then it says, give a reason. So we've already talked about that a couple of times. So hopefully remember what some of those reasons might be. But, you know, give me something that makes sense and is plausible, and I'll be happy with that. Or maybe I'll ask you for 2 reasons, right? Depends on what I decide for the test. You know, sometimes I like them to be neat. I want them all up to 20 marks. So sometimes I write the test and it's 19 marks, so I look for something else to add. Or sometimes it's 21 and I have to cut out a question, right? So kind of depends on where I'm at with the number of marks. Okay, so E actually tells you in the question what is involved in the hardness, right? So hopefully everyone remembers that for the hardness, we're looking at calcium and magnesium, right? But it tells you right in the question, it says use the multivalent cations, right? So, you know, that's a nice hint there thrown in the question. I may or may not necessarily do that, but read the question and make sure it does make sense. So remember, there were 3 steps for that, and the first step is already done for us. The first step was converting the concentrations into milliequivalents per liter, right? So we've already done that for the calcium and magnesium. We did that in step A. So step 2 is adding them up, right? So 9.25 plus 3.93. 13.3 milliequivalents per liter. And then the last step, we need to use the equivalent weight of calcium carbonate, and we're going to convert these milliequivalents per liter of hardness. So sometimes I will write down 13.3 milliequivalents per liter hardness, right? Meaning we've added up the calcium and magnesium. And so we need to convert back to milligrams per liter. So you multiply it by the equivalent weight, and that's going to give us 659. So that's some pretty hard water, actually, right? That's a lot harder than what you'd see in normal tap water, anyway. Okay, so one more question, which is the alkalinity. So we just did that last day. Remember the alkalinity? We're basically looking at the carbonate and bicarbonate. So first step is done already. We're converting everything to milliequivalents per liter. So you don't have to write that down, by the way. You can just show me the sample calculation. I'm just writing down the steps just as a reminder to everybody. But if you want, if it helps, that's fine, right? Whatever works. So you're adding them up. So in this case, you're adding 7.11 plus 2.28 for the carbonate, and that gives me 9.39. And then same last step as the hardness is we're basically multiplying by the equivalent weight of calcium carbonate, so multiply by 50, and we get 469. So you can see you're getting different numbers for hardness and alkalinity. So if you get the same numbers, you've probably done something wrong. Okay, so just another little hint there. Because you are looking at different things. Hardness, magnesium, calcium, and alkalinity, the carbonate, bicarbonate. Okay? So like I said, that's going to be about 10 marks, so half of your test will be a water analysis kind of question. Okay? Sometimes I throw in some written parts in there, you know, explain why or something like that. So be prepared for something along that lines. And you can see in this question here, we're talking about having a fussy client. And maybe I'll ask you a question about the fussy client, you know, why you have to explain this to the fussy client, or you know, the client asks you, the water is really hard, is that bad? You know, what does hardness mean? So there might be a question there where you have to describe what the negative effects of hardness might be, right? So just be prepared for something like that. Okay, so where are we? We are 1:30. Okay, we're gonna move on with some of the water biology stuff. But everything we start now will not be on the test. Fair enough? Okay. Okay, let's talk about bacteria. So this is, like I said, where the textbook was calling them plants because they have cell walls. There's just so many things about that I find offensive. So I did my PhD on the bacterial cell wall, so I have a lot to say about cell walls. You know, bacteria, you probably know, are prokaryotes, which means what? No, right? No organelles. No organelles, mainly no nucleus. So karyote actually means nucleus. So pro means before, so they're thought to be more primitive. U for eukaryote means true nucleus. So it's right in the name, pronucleus. You can think of it as no nucleus, pro and no rhyme, right? Prokaryote.
Is it true that bacteria are unicellular, meaning they only have one cell?
Yeah, pretty much all examples of bacteria that we know are unicellular. There are some that might form colonies, and those colonies might have cells that interact with one another in specific ways, but we're still considering them all individual organisms, right? So it's not like if you think about like a mushroom, you've got all these cells and they're forming a very unique structure, nothing fancy like that. So here's some of the ones that we're going to talk about. A very important bacterium is E. coli, Escherichia coli, and it is sometimes causing us to be sick, and it's also used as an indicator of fecal contamination. So we'll talk about that in a minute. You probably know a little bit about bacteria from David's class, as they're hugely important roles in the biosphere as decomposers and all sorts of other things, right? You know, we're living with them in our gut, they're on our skin, doing all sorts of cool things. So let's talk about E. coli. So mostly harmless. Okay, one of my biggest pet peeves is everyone's fear of E. coli. Every time you see it in the news, you know, like there should be a skull or crossbones or something like that, the way they use is depicting E. coli. The reality is E. coli is, most of the time, it's good for us, right? In fact, it's in our gut. It's all in our gut right now, in our intestines. And it's in there, and we're living together with E. coli, and it's a happy relationship, right? We are giving E. coli a nice, warm, moist place to live. We're stuffing ourselves with food. We're feeding it. E. coli is happy. And E. coli is doing good stuff for us. It's making niacin, which is one of the vitamin Bs. It's helping us to digest certain foods. And it's, for the most part, it's doing its job, and it's actually preventing, it's taking up space and preventing some pathogens from getting in there. So most E. coli is good, and you can see I call it mostly harmless, but there's many different varieties of E. coli, and some of them do cause us to be sick, and sometimes, that's a problem, right? And this is what we hear about. Everyone wants to talk about all the bad stuff, right? But I like to be a little more optimistic and want to talk about all the good parts of things, right? So like I said, E. coli is kind of an interesting biology lesson if you just think about E. coli, right? In terms of, what it even means to be a species. It's a really interesting question, but a huge majority of E. coli fall into this category. They're not going to make you sick, right? The E. coli that we have in the biology lab here, I don't suggest you do it, and please don't do it, I'll get in trouble. Don't drink it, but you probably could, and it probably would do nothing to you because it's not pathogenic. And all sorts of fancy names, geneticists, they like to give things names. You can see K12, DH5 alpha, and so on. These are the bad ones. You can see they have some fancy names, and I'll show you what those mean in a minute. Like EHEC is enterohemorrhagic E. coli. EP is enteropathogenic E. coli, and so on. And you don't need to know all the codes mean. That's fine. But these are the ones that you hear about in the news, or these are the ones that people go down to. Again, picking on Mexico, you go down to Mexico and you pick it up, right, from the drinking water. And these are the ones that are making people sick. There's kind of a third category of E. coli that are potentially pathogenic. So what does this mean? It means that if E. coli is in the right place and you know, you're happy, E. coli is happy, right? But sometimes there are scenarios where it gets into the wrong place. So sometimes people get bladder infections. So E. coli is good, it's all fine when it's in your intestine, but when it gets up the urethra into the bladder, that's very uncomfortable, right? And this happens quite frequently. E. coli can do this. Sometimes, you know, you can imagine all sorts of scenarios. There are scenarios in hospitals where, you know, due to some sort of invasive procedure like a catheter or surgery, people get E. coli in their blood, and that can be bad. But usually it's mostly harmless. But so we are going to focus on some of the pathogenic E. coli, but just really want to emphasize it's not a bad thing. E. coli is good. All right, what is going on here? Okay, so here is here's the list of a lot of those pathogenic ones. Did I skip a slide? Let me just go back. No, maybe I didn't. Like I said, you don't need to know the all the names here. Okay, but you can see that kind of in red there's a common theme and something we talked about already. How do we get pathogenic E. coli? Usually due to feces. And you can see most of these cases is actually due to human feces. There's one group here that's passed in animal feces, and unfortunately, actually, that's the worst one to get. But kind of that's a common trend as you can get in feces. You can see there's some other information there about it in terms of they might get different types of symptoms. Pretty much the main symptom, diarrhea. Right. So waterborne diseases, by the way, it's diarrhea and vomiting most of the time. Right, so some sort of gastrointestinal kind of symptom. Sometimes the diarrhea might have blood in it. Sometimes it may not, and that's kind of just differences in terms of the biology of these organisms, in terms of what type of toxins and how they cause the actual disease. And that's not so important for this class. But you can see there's kind of a list there of some of the different pathogenic E. coli. So I am going to talk about these a little bit, just to show you some of the differences, but I don't want you to get too much caught up in all the differences for this class. But there are a couple of things that I will highlight as we go along. So this is the one, these ETEC ones. These are the ones that that people will get when they travel often to poorer countries where the water sanitation is not as good. So, you know, I'm not picking on Mexico necessarily, but I am, partly because a lot of Canadians go to Mexico, right? In terms of, you know, sunny destinations, it's one of the most popular places to go. And I've actually known a few people that have gone to Mexico and they got traveler's diarrhea because they were drinking the water. I actually went to Mexico once, and that was the first thing they tell you when you get on the bus. Don't drink the water here, you Canadians can't handle it. Right? And that's true. You can build immunity to these things, right? If you get exposed to it a lot. It's just not a long-lived immunity. So this is passed in human fecal matter. And again, you know, it just has to do with, you know, less than standard water treatment, right? You can see this one here is common in infants in some of these countries, a little bit more susceptible to disease. So which countries are we talking about? Kind of this map here. So you can see that kind of the wealthier countries are having the better water treatment. And believe it or not, actually a big part of Eastern Europe, you're at risk The water sanitation systems there are old, really old. And so in some of those areas, it's advised that people don't drink from the tap and all that. And then some people a little more susceptible than others. I've seen different maps like this, and sometimes different countries are highlighted, and sometimes different countries are not. I know that I saw another map like this, and can't necessarily say this is the most accurate one, but the other map I was looking at, it was really a bit more, I would say, accurate, but it was super blurry, so I didn't want to show it to you. But it was showing South Africa actually was one of the was either yellow or green on that other map, and they're a richer country for the African continent, and a little bit more developed compared to a lot of the other places. So you can see there's more strains of E. coli to talk about. So word to the wise, when you are on Google Images search, be careful what you put in, right? You can imagine if you search for diarrhea, here is a nice sanitized picture for you, but be careful what you put. Anyway, so there's this EPEC. This is the one that's killing babies in a lot of countries. If you learn about water in certain countries, I think I was reading about can't even remember what it was. Maybe it was Zambia, and it was talking about this rural village, and it was kind of the day in the life of a woman there, and she's walking 1 kilometer to get to the stream. And kind of one of those typical things where the Africans, they love to carry the big jugs in their head and all that, and so she gets to the stream, and everybody is there, including their goats and their dogs and everything else, pooping in the water, right? The people aren't, but the animals are, and so she's bringing this cloudy water back to her home to do all this stuff, the cooking and drinking and all that. And this is pretty common in a lot of countries. Maybe not necessarily to that extreme, but like I said, this is why babies are dying in a lot of developing countries, is because of EPEC. Okay, so let's talk about EHEC. All right, so this is a good one to know. This is the one that when we see E. coli in the news, this is often what we're concerned about. This is the one associated with contaminated meat sometimes. There was it last year or the year before, there was a massive romaine lettuce recall across all of North America. Anyone remember that?
2 years ago.
That was maybe 2 years ago. I remember because I was really craving Caesar salads because I couldn't have them, right? Yeah, they were taking them off all the shelves everywhere, and it took them a few weeks to figure out where the contamination was coming from. And this is basically from cow manure, is what we're talking about here. So in the case of the romaine lettuce, what had happened was that there was a major supplier somewhere, probably California. I don't exactly know where it was. And you got this massive lettuce farm, and next door is a massive cow farm. And there had been an abnormal amount of rainfall. And so the flooding, went from the cow pasture over into the lettuce. And sometimes these bacteria will get in the lettuce, and it's not necessarily a cleaning issue. Sometimes the bacteria will actually get inside the tissues, so you can't clean it away. And so people were getting sick from it. But like I said, there's been a whole bunch of outbreaks over the years, all due to this one. You can see the big one that's listed in the middle is the 0157, and that's the one that we're talking about because people can get very sick, and if you're immunocompromised or you're really young, like a baby, or you're an older person, it can actually kill you. I think I've got a picture here but I had the picture of a cow for you, but you can see the spinach there as well. One of the questions people were asking me, I remember with this outbreak, is they're like, why is it always romaine lettuce? Because it's popular. That's pretty much it. Right, in terms of the vegetables on there, and it's leafy, so it's easy for stuff to get in there and get trapped, right? So this was a sign, I can't even remember where this was, and they're talking about E. coli 0157. And like I said, this is the one that can make you very sick and can give you a bloody diarrhea. And this is the one that if it gets into your bloodstream, if you are quite old or young, it can be fatal. And so this was this was what had happened in Walkerton. So if I remember correctly, Walkerton, it was the same idea. It was a flood. And it was some animal pastures, and it got into a town reservoir. And this was 20 years ago now, and it's actually amazing how much we've learned about this type of E. coli in the last 20 years. But there was another issue going on in Walkerton, is that people in the water treatment plant, they were, how shall I put it, not really trained in water treatment. They had been there a long time. They had been grandfathered in, and that, you know, now when new employees have to have a certain amount of training and all these kind of things, but they were grandfathered in, allowed to keep their jobs because of all, you know, this the evolving system, and literally they were ignoring samples that actually had tested positive for E. coli, and they said, oh, it's not that bad. And people died, and these people are now in jail, which is probably a good thing. But it was really sad. Like I said, 7 people died. I think more than 2,000 people ill, and it was a major news story that was going on for quite a number of months in the year 2000. So there's some pictures. Oh, there's our cow. I knew I had the cow. So here's something interesting we learned after that. I was talking to a researcher at the University of Guelph about this, and he got interested in coli 157. He started testing cows. And he was telling me that in one field he went, half the cows tested had it. So a lot of cows are positive, and it doesn't make the cows sick. So go figure. These kind of things happen all the time with microorganisms. They might make one person sick and not somebody else. And in this case, the cows are doing fine, but the humans are not. So watch out for cows. They look so innocent, but you know, they're just waiting to get revenge, aren't they? That's a joke. Okay, I'm just looking at the time, and I can see we've got, I'm not going to talk about these other organisms quite as much. I just want to mention Shigella and Salmonella, kind of because they're in a very, very similar situation as E. coli, although they tend to be a little bit more serious disease. So Shigella, it used to be named E. coli many years ago, but you know, at some point it got renamed. It's kind of like, you know, that it's actually kind of closely related to that 157. It will give you a bloody diarrhea spread by feces, you know, so I don't know why they didn't rename the 157 Shigella, because it's kind of almost not even E. coli. It's so nasty, but it's something else that comes up once in a while. Salmonella, you know, Salmonella is more likely to be found in animal feces. So if you have a pet snake or a pet turtle or a pet bird, so birds and reptiles, it's naturally part of their feces. So if you have a pet turtle or snake, wash your hands when done, you know, petting it and playing with it. And it happens, you know, it's usually a little bit more related to contaminated food, but it does happen in water once in a while. So before I finish, just want to emphasize, right, you know, these gastrointestinal things, we're looking at feces in water, leads to diarrhea and vomiting, and all those other intestinal problems that you might have, so cramps and things like that, and pain, of course. So I'm going to finish there today. We're going to come back and pick this up a little bit next day. Obviously, next day we'll have the test. Don't forget about that. Do take a look at the practice problems that are found on Moodle. And there's solutions there as well, so you can make sure you get the right answers, and you should be in good shape for next Monday's test.